Looks okay.
Yeah, okay, so now we have David Kolchmeyer, who's going to tell us about gravitational algebras in dS2.
Great, okay, yeah, so thanks so much for the introduction. And first of all, I'd like to thank the organizers of this wonderful workshop for giving me the opportunity to speak to you today. So the talk I'm going to give is entitled Gravitational Algebras in ADS2 and in DS2. And the first part of this talk is going to be based on a paper I wrote earlier this year. And the second part of this talk, which is some analogous story in DS2, is going to be based on some work in progress from Confluent. Also, this ADS2 story I'm going to discuss is also covered in a paper by Affiliation from this year as well. Okay, so generalized entropy has been a very useful tool in holography and quantum gravity, and in recent years it's been given a new algebraic interpretation. So the basic ideas that underlie the story appeared in papers by Kolchmeyer and Liu, and also Witten from about 2 years ago. And since then, there have been a number of follow-up papers, including some very interesting papers from this year that consider more general subregions and more general spacetimes. So to be generalized entropy, there's an area term. And so for this reason, it doesn't have immediate direct interpretation in terms of quantum microspace of the non-determinate theory of quantum gravity. Despite this, though, we still expect that generalized entropy does have an underlying statistical interpretation. And this is simply because generalized entropy still behaves like an entropy. For example, it obeys a generalized second law. Meanwhile, in the theory of von Neumann algebras, there exist traces on von Neumann algebras which obey all the formal properties of the trace, but still cannot be represented using this canonical state counting formula, trace of x equals the sum over the diagonal matrix elements of x. Here, this set of i's is the orthonormal basis. So this trace formula here I'll call the formula for a type 1 trace or a canonical trace. So there exist other kinds of traces that obey all the formal properties of the trace, like cyclicity of the trace or positivity of the trace, but these other traces don't take this form, and I will call them type 2 traces. So if we have a type 2 trace, we can define a type 2 von Neumann entropy. The formula for type 2 von Neumann entropy is the same, minus trace rho log rho, except now rho belongs to a type 2 von Neumann algebra, and the trace is a type 2 trace. And I'll say that this von Neumann entropy doesn't have an immediate direct state counting interpretation because it uses a type 2 trace, not a type 1 trace. Despite this fact, though, type 2 entropy still behaves like entropy. For example, it can be shown to obey various entropy inequalities. And so that's why we call it entropy. So I've introduced type 2 von Neumann entropy, and I've also discussed generalized entropy, both of which behave like entropies but don't have a manifest direct state counting interpretation. So it's perhaps not surprising, in fact, that generalized entropy is in fact a type 2 von Neumann entropy, and this was one of the essential results of the works discussed here. Good. So this perspective that generalized entropy is type 2 von Neumann entropy is actually quite powerful because it allows one to talk about generalized entropy beyond the semi-classical regime. So in particular, the papers I mentioned on the previous slide computed type 2 von Neumann entropy and made a match with generalized entropy. They did so for a particular class of semi-classical states. And these are states in which the fluctuations of the space-time geometry is very small. But in formalism, they also could have considered states where the fluctuations of space-time were not small. And so there are more general states that are not semi-classical. And I think that being able to talk about formally the entropy of these states, as well as compute the entropy in particular cases, could be useful in understanding the microscopic origin of this entropy. Of course, another way to generalize generalized entropy beyond the semi-classical limit is to use the Euclidean path integral. So we can prepare a state using the Euclidean path integral, and we can compute its type 2 von Neumann entropy, or we can just compute the entropy using the usual Euclidean path integral replica trick. And in this case, there could be various corrections coming from, for example, wormholes. And so an important open question is, how does this algebraic definition of entropy, which is purely Lorentzian, compare with the Euclidean path integral? So for an example where the Euclidean and algebraic entropies agree, you could look at, for example, JT gravity with matter, where the extremal entropy is set to infinity. I'll discuss this later in the talk, and this was also discussed in my paper and the Pennington-Witten paper. Furthermore, wormhole corrections were considered in the Pennington-Witten paper. There, the Hilbert space also contained the Hilbert space for baby universes. And the von Neumann algebra there acts on this Hilbert space and also agrees with, and its type 2 entropy agrees with the wormhole corrected entropy from the Euclidean path integral. There's also an interesting related paper by Junzhao Wang, where he basically was discussing the question, what is the von Neumann algebra whose entropy knows about the entropy that's computed via replica wormholes? And very roughly speaking, we could say that this von Neumann algebra is a free product of the algebra of the CFT and the algebra that acts on the radiation. So by doing a purely Lorentzian analysis where one analyzes the algebra of dressed operators in JT gravity with matter, one can deduce that the density of the black hole microstates takes this familiar form, sinh of 2 pi times the square root of the energy. This Lorentzian analysis was done in a paper by Josephine Su in 2020. And of course, at the time this was done, this density of states was already known from the Euclidean path integral. So a pessimist might say, well, perhaps this density of states was perhaps snuck into this calculation at some point, and then maybe she derived the answer that she wanted to get. But I think that this calculation was fully Lorentzian, and I'm going to employ a similar logic in this talk. So what I'm going to do in this talk is I'm going to study an algebra of operators that's dressed to an observer in two-dimensional de Sitter space. So one thing I want to emphasize is that this calculation can in principle be generalized to higher dimensions. That's because I'm not studying JT gravity in de Sitter. This is the only reason why I'm focusing on 2 dimensions is just to make the calculation simple. So in this talk, I will deduce the density of the microstates that accounts for the generalized entropy for the cosmological horizon of the observer, with the caveat that we assume that some version of de Sitter holography is true. And the setup that I consider was previously studied by the authors Chandrasekaran, Longo, Pennington, and Witten, and I'll describe a bit later what exactly I'm doing and how it differs. Okay, so here's a summary of what's to come. So first, I'm going to discuss the exact quantization of dS2 JT gravity with matter for the case where the extremal entropy is infinity. And the basic idea is that one can extrapolate bulk matter fields to either the left ADS boundary or the right ADS boundary, and these will define dressed matter operators. And these dressed matter operators can be used to define boundary algebras AR and AL. And these algebras emit a trace that reproduces Euclidean path integral computations. In particular, the algebras know about the density of states of the dual quantum mechanics. Okay, so then in the second part of the talk, I'm going to transition to 2-dimensional de Sitter space. I'm going to consider a massive scalar field theory and a pair of particles on a dS2 background. And the idea is that the particles carry clocks and function as observers. And so the setup that I'm going to consider is the same that was considered by the authors CLPW, but the thing I'm going to do differently is I'm going to exactly quantize their degrees of freedom, whereas in CLPW, the observers were traveling on classical trajectories. And then in analogy to what I will discuss in ADS2, I'll discuss how matter operators can be dressed to an observer and how the algebra of dressed operators knows about the density of states of the putative dual. Okay, so now I'm going to go into the first part of the talk where I focus on ADS2. So here's the metric for ADS2. and H0 is going to be the Hilbert space of a 2D Q of T. So now, if you want to talk about the Hilbert space of JT gravity with matter, it's very simple. It's just the Hilbert space of the Q of T, H0, times an extra factor of L2 of R. And L2 of R represents square integrable functions of L. L is the length, or renormalized length, of a constant time slice. So in particular, all the metric fluctuations in JT gravity can be encapsulated in a single additional mode, which is called L. Okay, so now let's talk about addressed operator in dS2, JT gravity. So here, if it wasn't for this L over 2 factor, this would look like the usual formula for the extrapolate dictionary. Phi is just a scalar field in the bulk evaluated on a constant time slice at spatial coordinate rho. And all we want to do is just evaluate phi at the right endpoint of the constant time slice. But this depends on the length of the constant time slice. So that's why this extra L over 2 appears here. So this is how I define OR, an operator just dressed to the right ADS boundary. And OL is defined analogously. Furthermore, acting on this Hilbert space, we have the left and right ADM Hamiltonians. So K is just canonically conjugate to L, and the formulas for these Hamiltonians are here. I won't need them later, but they're very simple, so I'll just write them down. Here, H, B, and P refer to the generators of the SL2R space-time symmetries for the Q of T that act on the H0 factor only. So now we can use the operators OR and HR to generate a von Neumann algebra, which I will call AR. And we can define the von Neumann algebra AL analogously. So a result of this work is that these algebras are type 2 infinity factors. And basically this means that they admit a unique trace up to a multiplicative constant. So this is how we're going to define the trace. Basically, we introduce the Hartle-Hawking state, which is in the Hilbert space, and it's defined by doing this Euclidean path integral. So on one boundary, the blue boundary, we put the usual Euclidean ADS2 boundary conditions, which includes the specification of a renormalized Euclidean length beta, which is dual to the amount of Euclidean time evolution on the boundary. And on this red boundary over here, we fixed this boundary to be a geodesic with a renormalized length L. And we also specify boundary conditions that correspond to the state of the matter theory. And then in the bulk, it's just a constant hyperbolic space. So we do this Euclidean path integral to prepare the Hartle-Hawking state. And then the trace on this algebra is just defined to be the expectation value of an operator in the Hartle-Hawking state in the limit that beta goes to 0. Okay, so this trace agrees with the Euclidean path integral almost essentially by construction. So for example, let's consider the 2-point function, which we can compute using the trace just by inserting this operator in the trace that depends on OR and HR. So it turns out that in the canonical formalism, there are multiple equivalent ways to compute this quantity. And the reason why I'm going to go over this in a little bit of detail is because I'm going to do something analogous in this de Sitter story I'll present later. So, so on the left diagram, for the part of the diagram below the dotted lines, that's where we basically we're just doing the path integral that prepares the Hartle-Hawking state on a constant time slice that's represented by the dotted line. And so that's what we have here, Hartle-Hawking of beta 1. And then on that state, we'll act with one insertion of OL and one OR. That's represented by these 2 red dots over here. And then we'll take the overlap of that with the top part of the diagram, Hartle-Hawking of beta 2. And this gives us the Euclidean 2-point function. But there's another way we can compute this. We can also start with the Hartle-Hawking state again. And then we can instead act on the right with OR, then do Euclidean time evolution on the right, and then act with OR again, and then take the overlap. And of course, it's manifest that both of these quantities will agree with the Euclidean path integral. Now you notice that this expression on the bottom here is not manifestly symmetric in beta 1 and beta 2, but because the trace is cyclic, it has to be. And this is a check that will also be done later in the talk in this de Sitter story. Okay, so now I'm just going to make a comment about higher point correlators. So Higher point correlators can be computed using a set of diagrammatic rules. I'm not going to go over all the diagrammatic rules explicitly, but I just want to give you a feeling for how they work. So on the left-hand side here, this is a Euclidean 4-point function where I have 4 operators extrapolated to the ADS boundary. And then this dotted line here just represents a way to cut this diagram in half on a constant time slice. And here we can insert a complete set of states. And it turns out that by doing this, we can derive a conformal block decomposition of the 4-point function. So this first diagram over here represents the case where the identity operator is exchanged. And then the second diagram over here corresponds to the case where where the non-trivial primary operators are exchanged. And what's interesting about these diagrams is that each diagram can be thought of as a Feynman diagram, in the sense that we can apply a set of specific diagrammatic rules to turn each of these diagrams on the right into an integral. And the integrand picks up some contribution from, picks up a contribution that corresponds to every point where 2 of these black lines intersect. And so this is how we can do the computation, and it gives us a very convenient way to analyze these algebras. In particular, the key properties we want to prove about the algebras AL and AR is that the commutant of AL equals AR, and furthermore, that the intersection of AL and AR is trivial, just consisting of multiples of the identity. And this can be done pictorially, and it's very nice, but I'm not going to discuss it in this talk. And an interesting consequence of this fact is that the algebras AL and AR together generate the entire algebra of bounded operators on this Hilbert space, which you can think of as the statement of bulk reconstruction. Any operator acting on the Hilbert space can be written in terms of operators in AL and AR in some limiting process. Okay, so now just to summarize the ADS2 part of the talk, we've defined an abstract trace on the algebras AR and AL, and these algebras are emergent in the SYK model. So by that, I just mean that we can represent the operators H and O in terms of the fundamental Majorana fermions of the SYK model. And furthermore, we can represent the abstract trace using the canonical type 1 trace of the SYK model, but crucially in the appropriate scaling regime. And so for this reason, we say that JT gravity with matter is dual to the SYK model. Now, if we didn't know about this, we could still infer certain properties of the dual from the algebras. So for example, to compute the density of states, we simply just compute the trace of some arbitrary function of the right Hamiltonian, which is just the expectation value in the infinite temperature Hartle-Hawking state, and then we can read off this density of states. And so in the de Sitter calculation I'm going to come to just now, one can also infer a density of states of the putative quantum mechanical dual by studying the algebra of operators. Okay, so if there are no questions up until this point, I'll move on to the de Sitter side of the story. Yeah.
It doesn't tell you how to define expectation values. You have to define a density matrix in the algebra in order to define expectation values.
Yes, so that's right. So the density matrices have to belong to the algebra. Yeah, so in particular, if you have a pure state, then you can find a reduced density matrix in the algebra. And
but for a given theory, you have to specify a particular.
so, well, is provided to you by the trace, like the trace furnishes a state. And so we can compute expectation values in that state and match that with the dual, with the bulk theory. Yeah, so you could use trace of 1, or you could construct any density matrix out of the operators OR and HR. Yeah. Okay.
Be a more basic question. So you mentioned, already in your opening slides that you want to, or you're giving a purely Lorentzian derivation, and you're not sure what the relations Euclidean is. But I would have thought that these these traces and entropies are sort of defined on particular states and therefore like in a fixed time slice. So I'm not quite sure where the difference, where the fact that the metric is Lorentzian is even coming into all.
Well, the full the full analysis here is just done by canonical quantization and Lorentz signature. And in the next part of the talk, I'm not going to refer to Euclidean path integrals at all. So this will be fully Lorentzian, everything about this. Oh, okay, yeah, we can discuss more later. Thanks. Okay, so we're interested in studying dressed operators or diff invariant operators in de Sitter. So in a closed universe, there are no asymptotic boundaries. And so what we're going to do is dress operators to observers. So this is the action for an observer. Basically, if you just focus on the second integral, this is the action for, the world line action for a point particle with mass m. And now what we're going to do is promote m to be a field on the world line and give it a conjugate, which I'll call p. And so then we have the standard action for m and p in the first integral. And I'm also going to use projections to restrict m to be above some lower bound. I'll come back to that specific lower bound later. Okay, so now let me summarize what CLPW did. So in CLPW, they considered a classical background that consists of a fixed de Sitter metric and fixed classical geodesic world lines for the two observers. One observer is sitting at the North Pole, one observer is sitting at the South Pole. I should say, actually, in their paper, they considered different setups, and I'm considering the one where there are two observers, one at the North Pole, one at the South Pole. The only degrees of freedom that are quantized are the clock degrees of freedom, P and M, as well as the quantum field theory that lives on this background. Now, we also have to gauge all the isometries of this background. And for us, this will be a single boost as well as the internal rotations. Of course, we should also gauge the discrete symmetries. Those are there as well, but in this work, that's not what we do. But it would be interesting to return to that. So what we're going to do in this talk is we're going to quantize all the degrees of freedom that appear in this action. And so this means that the observers are not part of the background. So now the background is just the de Sitter metric, and we have to gauge all of the de Sitter isometries, which for us in 2 dimensions will be SL1, 2. Okay, so we're going to work in 2 dimensions. So this is the de Sitter metric. So first, let me just talk about quantizing a single particle in de Sitter. So the Hilbert space of a single particle will be called H sub p, and we have to consider complex solutions of the Klein-Gordon equation of mass m with the Klein-Gordon inner product. So H sub p is going to be spanned by suitably chosen mode functions, which I call psi sub n. They're labeled by an integer n. And you can think of these mode functions as being analogous to, for example, e to the minus I omega t plus I kx in 4-dimensional Minkowski, where k is the momentum 3 vector. The idea is that since we only have one spatial dimension, which is compact, the spatial momentum is going to be labeled by a single number, single quantized number, which is just n. So using the Klein-Gordon inner product, I've normalized my mode functions in this canonical way. Now let's talk about the Hilbert space of 2 particles. So I take HP, tensor HP. Both particles have mass m for now. And so now we want to look for states that are invariant under the isometries SL1, 2. And it turns out that in this combined Hilbert space, there's a unique state up to normalization, and this is what it is. You might notice that the norm of this state is infinity. I'll come back to that issue later. But this is basically the unique state. And I think of this state as being analogous to the classical state of having 2 observers, one sitting at the North Pole and one sitting at the South Pole. Basically, this is because if you want to specify a configuration of 2 classical geodesics without reference to any particular reference frame for these isometries, there's essentially a unique way to do it, which is just to say that one geodesic is sitting at the antipode of the other. So likewise, in this quantum example, we're using the symmetries to fix this state. Okay, so now let me talk about how we're going to address a scalar field operator to a particle. So let phi of x be a scalar field operator, and let x mu of tau be the world line of a particle. So a naive and incorrect expectation is that the degrees of freedom x mu could be promoted to an operator that acts on the single particle Hilbert space. So this is incorrect. But if it were correct, we would say that addressed operator would just be evaluating phi at x, where x is the operator. But the reason why this is incorrect is because promoting the world line or the position, the space-time position operator, you can't promote the space-time position to an operator because the world line theory is a gauge theory with a constraint, and x of mu simply doesn't commute with p squared plus m squared, which is the constraint. So this is going to be the proposal for addressed operator. So here, if you focus on the second line, I'm taking my scalar field operator, and the scalar field operator kind of comes to us in the position basis, which isn't well defined. And I'm basically going to perform a Fourier transform to convert from the position space representation of this operator to a momentum space representation of the operator, which is better defined. And to perform this Fourier transform, I'm going to use my mode functions. And so basically, I'm just computing the matrix elements of this scalar field phi in a basis that diagonalizes the momentum, which is labeled by n and m. And so this is a proposal for an operator that's stressed to the particle, and I will test the proposal later. Okay, so now, until now, I was talking about quantizing a particle in de Sitter. What I'm going to do now is quantize the full action of the observer. So this means that all I have to do is I just have to take the mass, which used to be a parameter, and I just have to promote it to a quantum number. So now states are going to be labeled by the integer n for the mode function, and also the value of the mass of the observer. And also I mentioned that I'm going to take the mass to be above some lower bound. That lower bound is going to be 1/2. So it ends up being convenient to reparameterize the mass in terms of this other variable I'm going to call s. And s is going to be taken to be greater than or equal to 0. So my Hilbert space for the observer, H observer, is going to be spanned by these kets, and these kets are going to be normalized in this way, just by convention. Okay, so now the Hilbert space that we're going to consider will have a factor of H0, the Hilbert space of the QFT, as well as 2 copies of the observer Hilbert space, which I'm going to distinguish using left and right. And 0 is going to represent the Bunch-Davies vacuum. So this is going to be the definition of the Hartle-Hawking state. The matter is in the Bunch-Davies vacuum. If you focus on the sum over here, it looks like the same invariant state I mentioned earlier on in the talk. But now we're going to consider this invariant state for different values of the masses, and we can take a superposition of this for different masses. And this superposition is going to be represented by this integral over S here. And when we take the superposition, the relative coefficients between the different masses is not fixed. And so here it's represented by this function n of s, which I will specify later. Also, there's this parameter v, which we need to divide by. It's formally the infinite volume of SO1, 2. And this is just to give us a finite norm for the Hartle-Hawking state. Okay, so this is the Hartle-Hawking state. Now I'm going to upgrade my definition of addressed operator from before to addressed operator that can also induce non-trivial transitions between the different energy eigenstates of the observer. So if you focus on the second line here, it's the same integral I presented before, where I take the scalar field and the mode functions and do this Fourier transform. But now the 2 masses that appear in the mode functions can be different. And of course, what's really important is that this operator is invariant under the SO1, 2 isometries, and it is. And this is not the unique operator that I can define if I want to address phi to the observer. In particular, I could have inserted any function of S1 and S2 in this integral, and I would also get something fine. So basically, there are many ways we could address an operator to a world line. One way is to say, I want to evaluate the scalar field at the position on the world line when the observer's clock reads a particular time. But there are many other prescriptions one can use, and I'm just preferring to work in an energy basis. And for the purposes of generating an algebra, I'm just going to define OR to be like this, and it's gauge invariant. And OL is defined analogously. You just replace the R subscript with an L. Of course, OR acts trivially on the left observer Hilbert space and vice versa. Okay, also I'm going to define the operators MR and ML, which just measure the energies of the observers. So to get a Hilbert space, I'm going to start with the Hartle-Hawking state and then act with OR, MR, OL, and ML in all different ways. And then I can fill out a Hilbert space, which will be a subspace, an SO1, 2 invariant subspace. Okay, 5 minutes. An SO1, 2 invariant subspace of the Hilbert space I started with. And then on this Hilbert space, we can define the action. Well, we have the action of MR and OR, and then that will generate the algebra AR. Analogously, ML and OL generate AL. And in analogy to what I mentioned before, the trace is just going to be the expectation value in the Hartle-Hawking state. Okay, so up until now, I've given you a lot of definitions. Now I can finally present the results of some calculations that test the formalism. So let f1 and f2 be arbitrary functions, and let's compute this trace, basically the 2-point function. So I have two OR operators inserted. And so by definition, the trace is the expectation value in the Hartle-Hawking state. However, if the trace is going to be cyclic, I should be able to exchange f1 and f2 using cyclicity of the trace. So we would also want this to be equal to this second expression here. Likewise, we would also like to be able to compute this by inserting one OR on the right and one OL on the left. And of course, the order of inserting OR and OL shouldn't matter. Now, given the formulas that I've presented to you, the equality of all these things is not manifest, but it ends up being true if and only if this normalization function I've discussed before is equal to 1 over cosh pi s. So now the Hartle-Hawking state is completely fixed by the requirement, well, basically by symmetry and the requirement that it furnishes a trace, which I've checked for the 2-point function. So now we can finally compute the density of states, as I've discussed before. So I'll take the trace of some arbitrary function of MR. It's the expectation value in the Hartle-Hawking state. And so it becomes this integral over S. And you have two factors here. One is the square of n of S. As I've mentioned before, n of S is 1 over cosh pi s. And then we also get this other factor here, this S tanh pi s. This is the Plancherel measure of a principal series representation. And it basically comes out after formally regulating the infinity. I can discuss the details later if you would like. So now let's evaluate this density of states in the large mass regime. So basically, due to the 1 over cosh pi s squared, when the mass is large, you get an e to the minus 2 pi mass. And then from this Plancherel measure, you just get a factor of the mass. And this agrees with the semi-classical and one-loop calculation, Euclidean calculation, that was recently discussed in a paper by Whitten. Basically, if this hemisphere represents the Euclidean path integral you would do to prepare the no boundary state, we could also talk about what's the Euclidean path integral that prepares the no boundary state when there are two particles present. So in the classical approximation, we say that these two particles are at antipodes. So I've drawn them at antipodes here, and they can be connected by a geodesic. And now when I take two copies of this to compute the norm of the Hartle-Hawking state, basically I get a single geodesic world line that the observers can run around. And so the Euclidean action for this geodesic is just 2 pi m. And furthermore, one can do a one-loop calculation and get the factor of m out front. And so this is an example where this Lorentzian analysis I've presented agrees with the Euclidean path integral, at least in this limit. Okay, good. So if AR and AL are emergent algebras, analogous to the dS2 case, we expect that the quantum mechanical dual has this density of states. And if we compute high energy observables in the maximally mixed state, they would appear to be at finite temperature because the density of states has this Boltzmann factor, e to the minus 2 pi m built in. Okay, so now just to conclude, so I defined an algebra of operators that's stressed to an observer in two-dimensional de Sitter with a clock. The Hartle-Hawking state is fixed by symmetries and the requirement that it furnishes a trace, and this tells us the density of states of the putative dual. It would be interesting to generalize this calculation to higher dimensions. In principle, there's nothing stopping us, and 3 dimensions would be particularly interesting given some recent work here. It would also be interesting to study an observer in the bulk of ADS, since the whole theory is known to be dual to a CFT. So in this case, we can talk about the quantum mechanics that describes the observer and how it emerges from the underlying CFT description, whereas in de Sitter, we didn't have this underlying description. So you might ask, what is the CFT operator that's dual to the Hamiltonian of the observer? And this was considered in papers by Jafferis and collaborators. Okay, only one more comment. I should say that. Yeah, right. Okay. Thank you. Yeah, so as mentioned, only the continuous isometries SO1, 2 have been gauged, but in principle, we have to gauge all the isometries, including the discrete ones like CPT. And it'd be very interesting to do this following ideas that Daniel Harlow will be telling us about in this workshop. So that's all I have to say. Thank you.
So you said that there are different ways you could dress your field to the particles, and does that choice change what the NS function is, like the weights in the and even the algebras generated at the end, are they related by making different choice at that stage?
Yeah, so the different choices. Basically, I could take that operator OR and I could, multiply it on the left and the right by arbitrary functions of MR, and then I would get other dressed operators. So OR is to be viewed as a building block for other dressed operators. I should also say another way to get dressed operators would be to replace phi with like normal ordered phi squared. That's another way to get dressed operators. So really the algebra should be built using all of the dressed operators. And the cyclicity of the trace also works for replacing phi with normal ordered phi squared. And no, N of S, that's just part of the definition of the Hartle-Hawking state. That's not going to change.
This question is maybe a bit far afield, but could you dress the quantum field to a string?
The quantum field to a string.
You think of
So what was the last part of your question?
I mean, isn't that what you should do if you take ADS CFT seriously beyond the leading approximation?
Right. So yeah, this point particle model of the observer is definitely an idealization. So you could consider other models of the observer that perhaps might be more realistic. Like you can consider the observer to be a small black hole. That's what Jafferis and collaborators did. Yeah, so ideally, yeah, we'd like to have more elaborate models of the observer.
Are you saying that A left and A right are each other's commutant?
Good. So I haven't. So for this de Sitter case, I haven't formally proven that yet. So that's still work in progress. But
my question is related to the fact that in de Sitter, if you have a little bit of back reaction, you expect the diagram to be a little taller.
Right.
So if you send the signal from the left to the right, and the right one sends a signal, you would expect that they can communicate. So that seems to be consistent with the idea that you could A left and A right would be each other's commutant.
I see. Okay. Okay, yeah, so well, that's not something I've shown. Just in that, yeah, I've only analyzed these algebras at the level of the 2-point function. So I don't know what happens for higher point functions, and I haven't tried more elaborate calculations. Yeah.
That's hard to address in general because you don't have the two boundaries. So yeah, there's no reason why they should really be commuting.
Right. Yeah, I didn't know what the claim was. So.
Right.
De Sitter space, you can't put more than a finite number of massive particles into three-dimensional de Sitter space because they close up the space-time.
Right.
So the idea of a massive quantum field in three-dimensional de Sitter space doesn't really make any sense.
Right. Yes. Yeah. So this was certainly an idealization. So the only aspect of this calculation that made it gravitational was that I was gauging the space-time isometries. So the back reaction was not considered here. So yeah, the idea that you could excite as many particles as you want is an idealization for sure. Yeah.
That's the same as the Nari in higher dimensions, right?
Sorry. Yeah. Sure.
You just can't put too much stuff in the
Right.
Anyone else? All right, well, here we are back on schedule, so let's be back at 11 for the next talk.